Okay, so let's get started. Um, Hello and welcome everyone to week 7 of Fundamentals of, for Convective Heat Transfer. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of IIT, from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. So let's dive in. We will first take a look at question number 1, which is a simple one, just asking us for the definition of what Grade's number is. Is it option A? Is it x by d over Reynolds number times Prandtl number? Is it option B, Reynolds number times Prandtl number over x by d? Or is it Reynolds number times Prandtl number divided by xd, x times d? Or is it the reciprocal of it, that is x times d over Reynolds number times Prandtl? So Grade's number is an important number, non-dimensional number used in the study of developing flows in the context of uh, convective heat transfer. So the value of Grade's number is something that is important and that tells us uh, whether we are in the developing region or in the developed region, and development comparative developments of hydrodynamic boundary layers as well as thermal boundary layers. So if we take a look at the solution, it's actually option A, that is x by d over Reynolds number times Prandtl number. So oftentimes it is also, sorry, I think this is wrong. It should be option B. So oftentimes the inverse of this Grade's number is used as a stand-in for the entrance length as well. So since you see that there's a x over d in the denominator, so that's why we can say that, you know, the reciprocal of it would be x over d times 1 by Reynolds number and Prandtl number. So this is just a scaled version of this term, x by d, and that is something which should be proportional to the entrance length, right? So another uh, interesting aspect of this Grade's number is that upon some further simplification, if we replace Reynolds number by uh, if we replace Reynolds number in terms of its components, that is velocity, length scale, and viscosity, and we do the same with Prandtl number as well, we will get something like this. So we will get this d over alpha, we'll get d square over alpha divided by, mm, we will get something like, um, okay, let's do this thing. So mhm, u if I bring now, so it will be x by u infinity, which is the free stream velocity or some characteristic velocity of the flow. So you see these, both the numerator and the denominator, they have the units of time. So I have some time, so tau t by tau, let's say f. So this is basically the thermal time scale, which means it's the time taken for some heat to diffuse across length d. So you see d square by alpha. Alpha is the thermal diffusivity. And the denominator, it is another time scale, which is x over u. So you can see some distance divided by velocity. That also gives us some time. So, and that is the hydrodynamic or the flow time scale. I'll just call this, sorry. So I'll just call this flow time scale. That's the time taken for a fluid parcel to move across a distance x. So the relative magnitudes of these times taken actually gives us a feel for what kind of a flow situation flow situation we're dealing with. So if the thermal time scale is much smaller, that means heat transfer is occurring at a much faster rate than the advection of the fluid, whereas the reverse would mean the flows are much faster than the rates of heat transfer. And that tells us the importance of which uh, boundary layer, hydrodynamic or the thermal boundary layer, are more developed. Right. So this becomes important in the context of developing flows. Right. So moving on, we'll move on to look at the definition of another important non-dimensional number in this context, known as the Brinkman number. So there are again four options given here. You have to pick the correct one. So is the Brinkman number equal to mu u square upon k delta t, where delta t is the temperature difference, k is the conductivity, mu is the coefficient of viscosity, and u is the uh, velocity scale, some characteristic velocity of the problem. So that was option A. Or could it be option B, k delta t over mu u square, or option C, mu u square over Cp delta t, where Cp is the coefficient of, or sorry, Cp is the heat transfer, sorry, it's the heat capacity at constant pressure, or is it option D, Cp delta t over mu u square? Which one should it be? Okay, so let's take a look at the solution. It's actually option A, that is Brinkman number equal to mu u square over k delta t. And once again, Brinkman number is also another important number which shows up in the study of heat transfer in co-ed flows. So this basically, the Brinkman number is the product of the Prandtl number into the Eckert number. So Prandtl number, again, we know that it is equal to mu by alpha. These are the relative diffusivities, and the Eckert number, which is basically a representation of the it represents a ratio between the heat transfer by conduction. So how do I write this? So let's see, mu u square by k delta t is equal to this thing, mu over alpha times the Eckert number. So Eckert number, if we try to simplify, we will get u square by k delta t into alpha over mu. So this divided by rho gives me mu. Mu is basically, sorry, so this will give me a rho, and alpha can be written as k by rho Cp. So alpha by k is basically 1 by rho Cp. Rho also cancels out. So what I basically have now is u squared over Cp into delta t. And yeah, so let's just keep the rho for a while. So we'll keep these rows. So this basically is the, you know, energy contained by convection, and this is the thermal energy, rho Cp delta t. So these are both physical quantities which have the same units as energy, and the Eckert number is basically the ratio of those two. So in case I have a flow, uh, what how much energy content is contained within the flow? So not just convection energy, this is basically uh, the energy contained by the flow, right? So this is something like a dynamic head that we see in Bernoulli flows. So that's the energy contained in the flow itself, the kinetic energy. So instead of calling it convection energy, I'll correct myself and call it the kinetic energy of the flow. bulk kinetic energy. And reciprocal is the thermal energy, that is the individual kinetic energy. The sum total of that is what temperature is, or what thermal energy is. So that is the thermal energy. So in case there is a flow, it has some energy, and what parts of those energies are contained as kinetic energy or as thermal energy, we get to know that through the Eckert number. So this again becomes important, especially in the cases where there is a huge uh, viscous dissipation, where a lot of the kinetic energy of the flow gets converted into thermal energy due to friction. And a very high temperature gradient co-ed flow is one such example. So we'll look at that later. Let's move on to question number 3 now, which is asking us that for uniform heat flux condition, the value of Nusselt number for hydrodynamically developed but thermally developing flow in a circular duct. So these are all important uh, pieces of information. So a circular duct is important, a thermally developing but hydrodynamically developed flow, and in the case of uniform heat flux condition, what is the value of Nusselt number in that case? Is it option A 3.614? Is it option B 3.66? Is it option C 4.021? Or is it option D 4.36? So let's take a look at the solution. It's actually 4.36, and it's the same Nusselt number that shows up for the uniform heat flux condition and fully developed. That is both uh, hydrodynamically as well as thermally developed flow. So the numbers in the end becomes the same because we saw in the sorry, because let's say if I try to draw a plot for two cases. So this is, let's say, the saturation value at 4.36. This is what Nusselt number is, and this is what x by d is. So x is basically the axial direction in a circular duct. So this is x, this is r, right? So in this context, what is my variation of the local Nusselt number as a function of the some unit of distance? We non-dimensionalize with the diameter to just to generalize it. So in case of a flow with the uniform heat flux condition, it starts out high and then finally saturates and becomes equal to 4.36. So this number therefore is the same for thermally developing as well as thermally developed and as well as hydrodynamically developed circular duct with uniform heat flux condition. And in case if it was a uniform wall temperature condition, in that case our answer should have been 3.66. Okay. All right, so let's keep moving. We'll move on to question number 4, which is asking us to first of all consider two statements about it, and then if we go down and take a look at the options, we see it is asking us to pick out which ones are correct, whether only one is correct, only two is correct, if both are correct, or if both of them are wrong. There is none of them are correct. So let's take a quick read at the sentences, the statements. So the first statement says that if Brinkman number is greater than 4, then temperature rise is due to temperature rise due to dissipation. What I mean by dissipation here is viscous dissipation. It is often represented by a capital phi. So if the first statement says that if Brinkman number is greater than 4, only then this phi becomes important. And the second statement says that if the Brinkman number is important in case where a large velocity change occurs over short distances. Meaning, once again, large change in velocity over short distances simply means that the velocity gradient is high. So I have some u over some y. It could be x or anything else, doesn't matter. Some velocity over some distance, this being very, very high. So in given these two statements, which ones do you think are correct? All right, so let's take a look at the sorry, let's take a look at the solution. It's actually option C, that is both 1 and 2 are correct. See, first of all, let's look at statement 2. So we already explained that large changes over short distances simply means that these gradients are high, and that itself causes a high value of the viscous dissipation, and that's where it becomes significant. So, and this Brinkman number greater than 4 really has another significance. So if we take a look at a quid flow, where the we have flow between two parallel plates separated by a distance, let's say h, and the top plate moves with a velocity u, and the bottom plate is stationary. So we may have a velocity profile like this, which is linear, and so that's not what we'll focus on now. We'll focus on some temperature profile, where let's say this is at some temperature Th, and this is at some temperature Tc, that is T cold. We're assuming that the top plate has a higher temperature. So for low Brinkman numbers, especially Brinkman number 0, we get a linear profile like this. This is Br0. Let's say red means Br equal to 0. Now let's use another color. So in case when Br becomes larger, we'll just call Br equal to 4. In that case, there is no energy transfer between the flow and the top plate. So this velocity gradient here disappears, and there is a higher gradient over here. So this is what Br equal to 4 means. Now if we keep increasing the Brinkman number, we get some Br greater than 4. The viscous dissipation is enough to increase the maximum temperature within the flow even above the higher temperature of the two walls, that is Th. So we can see that here, due to viscous dissipation, there is a higher temperature at this point within the flow, which is created due to the shear stresses and friction, uh, allowing the kinetic energy of the fluid to get converted into thermal energy, and as a result increasing the temperature of the fluid even above the higher of the two temperatures of the walls, that is Th. So this is when the temperature rise due to dissipation becomes really significant. So that's why both statements 1 and 2 are indeed correct, and we should have chose option C, that is both 1 and 2 are correct. I hope that makes things clear. We will move on to question number 5, which is true or false type of question. And the statement is that Eckert number is the ratio of momentum diffusivity to thermal diffusivity. Is that statement true or is it false? Let's take a look at the solution. It's actually false. So we already know what the ratio of momentum diffusivity to thermal diffusivity is, right? So it's basically the Prandtl number. Eckert number, on the other hand, we saw is the ratio of the kinetic energy to the thermal energy. Where rho basically disappears, so all that remains is q square by Cp delta T. So what is it the ratio of? It is the ratio of the kinetic energy to the thermal energy. All right. So this was a simple one. We'll move on. We'll move on to question number 6, which is asking us to match the following for fluid flow with viscous dissipation. So in case there is viscous dissipation, what is the Reynolds number at the bottom wall and at the top wall? So once again, this is what a fluid flow looks like. There are two parallel plates with some separation between them, and one of the plates is moving with some velocity u, and the velocity profile is always linear in case there is no pressure gradient, and there will be some temperature profile set up according to the Brinkman number as we saw earlier, and this is what the Brinkman number is, this product of Prandtl and Eckert. But anyway, here our focus is different. Here we want to know that in the bottom wall there is some heat transfer due to which there will be a Nu bottom, that is the Nusselt number at the bottom wall, and similarly at the top wall we will have a Nu top, which is the Nusselt number for the top wall, expressed in terms of Prandtl number in Eckert number as shown in this second column. So we have to match the options from the first column to the second column. So is it so which ones should it be? The two options here are 2 minus Prandtl number into Eckert number, or is it minus of whole 2 plus Prandtl number into Eckert number? That is minus 2 minus Prandtl number into. And there are two options given below. It could be either A1 B2 or A2 B1. Let's quickly take a look at the solution. It's actually option B, A2 B1. So basically uh, Nu at the bottom is, so there heat transfers away from it, so that's why the uh, values are negative. So it's minus 2 minus Prandtl number into Eckert number. Sorry, I said it wrong. So in the, if you look at this way, the top is hotter and the bottom is cooler, so heat usually flows from the fluid into the bottom wall. That's why the heat flux over there is negative, is less than 0, and is given by minus 2 minus Prandtl number into Eckert number. Whereas this one, the Nusselt number at the top is equal to 2 minus Prandtl number into Eckert number. So at Brinkman number exactly equals 2, it would become 0. We saw earlier that the temperature gradient becomes 0, and then as it increases, so as it increases, then it will keep on increasing. Sorry, then it will become negative, as we saw earlier that the fluid becomes hotter due to viscous dissipation, and even the top wall uh, receives heat from the flow. So I think I should go back and correct myself. So this number, Brinkman number greater than 2 is enough for the temperature rise due to dissipation becoming significant. These limits should have been 2 instead. Sorry. And how did we get informed of that? We got informed from these two formula, which we can attain analytically itself. So 2 is the what can I say, a threshold below which Brinkman number, if Brinkman number is below that, then we have the top wall being the hottest region of this whole configuration and heat coming out of it. If Brinkman number gets greater than 2, then we have the fluid becoming the fluid attaining the maximum temperature, and it transfers heat from it to the top wall as well, which is the hotter between the two walls. I hope that makes things clear. So we'll move along. We'll move on to question number 7, which is asking us that for a hydrodynamically fully developed and as well as a hydrodynamically developing flow through a circular duct with constant wall temperature, what is the value of Nusselt number at x equal to 0? So for both cases, that is when it is hydrodynamically fully developed as well as hydrodynamically developing, uh, what is the value of the Nusselt number at x equal to 0? Is it option A 0? Is it option B 3.66? Is it option C 4.36? Or is it option D infinity? And remember here Nusselt number, I'm talking about the local Nusselt number. At x equals 0. So let's take a look at the solution. It's actually infinity. So earlier we saw the expressions of the local Nusselt number as a function of x being something like this. So where here it attains, it keeps decreasing and is finite, but exactly at x equal to 0 it is infinite. So this line doesn't really touch anywhere. But that is again theoretical, because x equal to 0 is really not a finite amount of uh, material. It's just one point, or in case of a boundary layer as well, if we look at this, so x starts from here. This is what x equal to 0 is. That's basically one point. In case of a circular duct, it will be just one circle without any thickness. So the heat transferred from it is not really infinite, but the Nusselt number, there is a density of heat transfer, sort of. The density of heat transfer to that is infinite. So we will see this for finite values as well. If we do not go to x equal to 0, but very small values of x, that is at, let's say, 10 power minus 3, or if we can go even smaller, we will see that these Nusselt numbers are very, very huge, the local Nusselt numbers, because there is a huge gradient, and uh, so is the flow gradient high as well as the temperature gradient is high, which means that the rate of heat transfer would also be very, very high. Okay, so moving on, we'll move on to the last question of today's session, question number 8, which is asking us that for fully developed flow through a circular duct, what is the non-dimensional velocity profile U star? So U star is the non-dimensional velocity given by U over UM, that is mean velocity, and we define a non-dimensional radius as well, which is dimensional radius r over r naught. So here the main keyword is that for a fully developed flow through a circular duct, what is the non-dimensional velocity profile? Is it option A, U star equal to 1 minus eta squared, or is it option B, U star equal to 2 into 1 minus eta squared? Is it option C, U star equal to 3 over 2 into 1 minus eta squared? Or is it option D, U star equal to 2 into 1 minus 2 eta squared? Let's take a look at the solution. It's actually option B. This is actually very simple to do. So for circular ducts, we have seen that U is equal to 2 um, or rather we can write this as U max. It attains a parabolic profile which looks something like this. Okay, this is Hagen-Poiseuille flow. Sorry, through a circular duct like this. We've seen that it takes a parabolic velocity profile like this. We're all very familiar with it. And the equation of this is given by this. Now, another thing we know is that this u max, the maximum velocity which it attains over here at r equal to 0, that is equal to twice the mean velocity. So if we replace that, so u is equal to 2 um into 1 minus r square over r naught squared. Now it's a matter of simplification. So I take this um to the denominator and it becomes u star, and this 2 remains. It's 1 minus, once again, r over r naught is eta, and they are both squared, so this becomes eta squared, and this is what we get. And that is indeed option B, and it's the correct solution to this. Okay, so that's all. Thank you. We'll meet each other again on next Tuesday from 6 to 7.